Hey guys, welcome to your Monday lecture. Apologies for the weaker sound quality today. I found out my headphones were drained of energy, so I'm having to use my computer audio instead. Never mind, it'll be all right. So looking at chapter 3, because let's start off with an idea of the kinds of chemistry that we could face in medicine with a couple of scenarios. So from the previous chapter, we talked about a researcher asking you for a suggestion of an element that was similar to lithium. Of course, that would be an element in the same group, one of the other alkali metals, as they have very close chemical properties within a group. And so apparently this researcher has come back and now wants you to suggest a way of making one of their drugs more water soluble. This is important in medicine because many drugs reach a target organ through the bloodstream. There's a lot of water in your blood. And so if you can make a drug water soluble, you make it possible for it to be transported through the bloodstream. And there are certain drugs which almost guarantee water solubility, and we'll talk about them in this chapter. Then later on, you've got a patient who is diagnosed with hypertension, and they ask for your advice on chemicals which they know are in their diet, chemicals which might be good or bad for their hypertension. And they want to know about things like glucose, monosodium glutamate, sodium nitrite, pectin, sodium benzoate, and potassium chloride. Some of these compounds have no effect on hypertension, but some are good at lowering it, and some are very good at raising hypertension as well. So which is which? We'll talk about that. So in chapter 3, we're looking at bonding between one atom and another. And if everything else was equal, those two atoms would come together, literally shake hands by overlapping their orbitals, their shells of electrons, and share electrons, negatively charged electrons, which would now feel a mutual attraction to the protons in each nucleus. Attracted to one nucleus, attracted to the other. And so that attraction for the protons in each nucleus would form a chemical bond between the two atoms, what we call a covalent bond. However, things are not always equal in chemistry. And we know about this already from chapter 2 because we've looked at the atom's ability to attract electrons, what we call the electronegativity. And there are two steady trends in the periodic table. One was from left to right. As we move to the right, we've got elements with an increasing number of protons and therefore form an increasing attraction for electrons. Its own electrons and therefore shrinking the size of the atom, but also an attraction for other atoms' electrons if they are joining together in the shells and sharing that orbital space. We also saw an increase in attraction for electrons, an increase in the electronegativity as we moved up the group. That's because we were stripping away shells, stripping away layers, and so the electrons were now physically closer to the nucleus if we were dealing with an atom with fewer shells, a smaller atom. And so those two ideas combined, it's quickly easy to see that the non-metals are very good at attracting electrons because they're the ones with the most protons on the right and the ones with the least shells at the top. While the metals have less protons in general and also tend to have more shells. And these two ideas, as we compare a bond between a metal and a non-metal, always allow the non-metal to win. There's going to be a transfer of electrons from the metal to the non-metal. And so instead of sharing electrons to make chemical bonds, the atoms exchange electrons and ionize. And this is our chemistry of chapter 3, ion chemistry. The metal, if we assume the element on the left here is the metal, losing electrons and becoming positively charged because it now has more protons than electrons. Not because it gained protons, but because it lost electrons. And the non-metal, taking those electrons from the metal, it now has more electrons than protons and is negatively charged. And it's those electrostatic attractions, positive to negative, which hold these ions together in ionic bonding. So let's take a look at an example and see how it works. For example, an atom of lithium combining with an atom of fluorine, a metal and a non-metal. Now, both atoms start off electrically neutral. The lithium with free protons, but it also has free electrons, so no charge. But it does have one electron in its second shell, in that 2s subshell. That's the electron furthest from the nucleus. That's the electron most vulnerable to being taken because it has the weakest attraction to the protons in the nucleus, being in the second shell. Meanwhile, the fluorine at 1s2, 2s2, 2p5, it just needs one more electron to complete its set. And it's going to grab that electron from the lithium because as its element number 9, atomic number 9, it's got 3 times as many protons as the lithium atoms. So it takes that electron out of the shell of the lithium and uses it to complete its own shell. And we form these ions with electrical charge. That's all we mean by ions. There's an imbalance between protons and electrons, and therefore the metals having lost electrons are positively charged, and the non-metals having gained electrons are negatively charged. We always see the ions form in this way. Metals lose electrons, non-metals gain electrons, because the non-metals are fundamentally better at attracting electrons. So the ion of lithium produced has emptied its outer shell and now only has electrons in its first shell. And that's a shell that was already complete. So it's like a complete set of Pokemon trading cards for the lithium. Its new outer shell, its new valence shell is the first shell, and that's a complete shell. And that imparts a great deal of stability on the lithium metal ion. Likewise, with the non-metal having picked up that electron from the lithium, that completes its set. It is a complete set of Pokemon cards as well, and that also makes the non-metal fluoride very stable. And this is always the trade-off between the metal and the non-metal, which imparts stability and allows the chemical bond to form. Both metals and non-metals now have a completed outer shell. The metal by erasing the electrons from its outer shell, and the non-metal by using those electrons from the metal to complete its outer shell. The lithium with 3 protons but now just 2 electrons has a 1+ charge, and the fluoride with 9 protons but now 10 electrons has a -1 charge. And the ions we see is always based around that strategy to complete their shell, just like the elements in group 8, the noble gases. When the shell is complete, we have stability, and they don't have to do any more Pokemon card trading. They've got their set. They've got their complete shell of electrons. This is always a guideline for most of the elements when they try and become ions. How many electrons does the metal lose in order to back up and look like the element at the end of the previous row in terms of its electrons? And how does the non-metal gain electrons to complete its shell like the element at the end of its row? So stability comes through completing the shell. What we sometimes call the octet rule, because the majority of the elements in the early part of the table are looking for 8, just like neon or argon. So that's our split. It's a metal bonding with a non-metal. The metals lose electrons, the non-metals gain electrons. That's the only kind of chemical bond we're looking at in chapter 3. We're not looking at metals with metals, that's a higher level of chemistry, and we're not looking at non-metals with non-metals. We'll deal with that in chapter 4. So we can look at the position of the element in the table and figure out its electrical charge. So for magnesium, it's the second element in the third row of the table. And of course, the position in the table tells us how many electrons the atom has in each shell. 1, 2 electrons in the first shell, lithium through neon, 8 boxes, 8 electrons in its second shell, and for the magnesium, just 1, 2 electrons in its third shell. And so for the metal, when it ionizes, it wants to empty that shell, get rid of 1, 2 electrons, so that the magnesium backs up to neon in terms of its electrons, which is the element at the end of the second row when the second shell is complete. So a 2+ charge for magnesium, and that works out from the math. 12 positively charged protons, but only 10 negatively charged electrons left, just like neon, element number 10. It's a 2+ charge. Electrical charge is always just the basic math between electrons compared to the protons. Similarly, when we look at aluminium or aluminum for our American friends, it's the third element in the third row. It's got 1, 2, 3 electrons in its third shell. It's a metal. It's going to bond to a non-metal. We don't necessarily know which non-metal it's going to bond to. We don't really care at this point because we know that the metal always loses. It's losing 1, 2, 3 electrons to empty its shell. So moving 1, 2, 3 boxes back for an electron configuration like neon again. It's still an ion of aluminium because it's got 13 protons, but its electron count looks like neon with a completed second shell. Again, 13 positively charged protons compared to just 10 negatively charged electrons. Oh, excuse me. Oh my goodness. It gives us a charge of 3+. So the metals empty their shell. And we can read that off the periodic table given the position of the element each time. Looking at non-metals like oxygen, because being a non-metal, it's going to gain electrons to complete its shell. If it wants to look like neon, it needs 1, 2 more electrons as we move 2 more boxes. We've already counted the oxygen box. If we hadn't, we'd be back at nitrogen. So we've counted that oxygen box to get there. So 1, 2 more. So a charge of 2- for the oxygen ion, oxide. Because it's 8 protons, but 10 negatively charged electrons like neon. Looking at phosphorus down below. Same tactics, there we are. It's a non-metal, so it wants to reach the end of its row. We need to count 1, 2, 3 more boxes. That's 3 extra electrons, a total of 18, like argon. So a -3 charge. So we can use the position of the element in the table, metal or non-metal, to recognize the electrical charge in most cases. One exception to this is the transition metals in the middle of the table, but we'll talk about them another day, either Wednesday or Friday this week. So with these metals and non-metals ionizing, we can write equations to show that ionization. So for example, the sodium, start off with the sodium chemical symbol, Na. We draw in our arrow to tell us that there's a chemical change taking place. Now from the position of sodium in the table, let me quickly revert back to that. First element in the third row, it needs 1 electron to be erased from its shell, to empty it, to leave it looking like neon. Remember, the metal is always losing electrons. So from that table position, we know it's going to be a 1+ ion. And so we then add that electron back into the equation when it's no longer part of the atom. Sodium, starting with 11 protons and 11 electrons, hence neutral. After the ionization, it's a 1+ charge because it now only has 10 electrons. So the electron missing at the end is added back into the chemical equation. Electrons lost by the metals always appear on the right-hand side of the equation. A similar story when we look at something like potassium. Potassium atom is a group 1 element like sodium, so it's going to be a 1+ ion as we remove its 1 electron, and that electron missing we add to the right-hand side of the equation. Similarly with aluminium that we'd also looked at earlier, 13 protons and 13 negatively charged electrons, but we want to clean out those electrons in its outer shell as it bonds with the non-metal. So losing those free electrons, we put them into the equation when they're gone. You always see the electrons when it's no longer part of the atom. Like you can see my car keys when I finally take them out of my pocket. No longer on my person, the electrons no longer in the shell, we show them in the equation. The electrons which appear at the end are electrons lost. They were there to begin with, but they were part of the atom, in its pocket or in its shell. And that's why the atom begins without any electrical charge. We can pull the same trick with a non-metal. So nitrogen, the 5th element in the 2nd row, we need 3 more electrons to complete its octet like neon. And so it's going to be a charge of 3-. So for the electrons which have been exchanged, the nitrogen doesn't have the electrons at the beginning, it just has them at the end when that electrical charge forms. So the electrons being gained are added on to the beginning of the equation. 3 electrons and the nitrogen to give us this nitride ion.
Mommy,
Hello. You want to say bye to Kitty Cat?
No.
Okay, you want to say good night to me?
Do we know? I have something.
You have something? What do you have?
Here's the boo.
Oh my goodness, that is a bad boo-boo. Can I kiss it?
No. It'll hurt when you kiss it.
Oh, it hurt. Okay.
And I got a scratch.
Funny how it
on my leg.
doesn't hurt when Mummy does it. Oh, you got a scratch too. Okay, I will just leave it alone. Say good night. Or not. Let me get rid. Let me get my daughter to bed and I'll come back.
Are you?
All right, safely in bed. So, nitrogen, non-metal, so we know it's picking up electrons and picking up enough electrons to complete its shell. That gives it a 3- charge. Oxygen, 2 boxes shy of the end of the row that it's in, needs 2 electrons to complete its shell. It finishes with a 2- charge. Fluorine, 1 box shy of the end of the row it's in, needs 1 electron and have a 1- charge. Let's see, what else do we need to do tonight? So let's look at some practice questions while we're here. Kind of thing we could see in a chapter 3 exam. So write down the electron configurations for nitrogen and its different forms here, or implied different forms. And would they be stable? So the nitrogen atom itself, just based on its position in the periodic table, would be 1s2, 2s2, 2p3. Nitride ion we've been talking about, 3 minus. That'd be 1s2, 2s2, 2p6 with those extra free electrons. And finally nitrogen, 4 minus, 1s2, 2s2, 2p6 because 6 electrons completes that subshell, and 3s1. Now which of them are stable? Well, the nitride, 3 minus, that's the only one which would actually be stable because it's the only one which implies that the outer shell is complete. That is not seen with anything except the nitrogen 3 minus ion. Next one's predicting the electrical charge, just a pure math of it. 13 positively charged protons compared to 10 negatively charged electrons. That would be a charge of 3 plus. Incidentally, when we write charges in ion chemistry, you write the number, then the charge when you're writing it. 16 protons but 18 electrons. Again, the pure math of it. 16 minus 18, that would be minus 2, but we write it as 2 minus the number, then the charge. Then a neutral atom with an equal number of protons and electrons, which then loses 5 electrons, that would be a charge of 5 plus. Let's look at the next ones. And again, you can always pause the video as we're going through these and try them for yourself before revealing the answers. So similar to what we had in chapter 2, looking at protons, neutrons and electrons, but now of course there's an electrical charge. Number of protons, that's from the atomic number of course, 20 for calcium, 17 for chloride, 25 for the manganese. Number of electrons, well, based on the charge, 2 plus is 2 more protons than electrons, so there's only 18 electrons. Charge of minus 1, that's a surplus of electrons, so we're 1 more and up to 18 electrons again. And then for the plus 5, minus 5 electrons from the 25 we started with, so just 20. And the number of neutrons, as we did in the last chapter, mass number minus the atomic number gives the number of neutrons, so 20, 20, and then 30. Let's look at these last questions on ionization of these elements. Clear my screen up a bit. Get it just right. Okay. So if we look at a periodic table, just to remind ourselves, remember in an exam you'd always be given access to a periodic table. So the cesium and cesium in the table, group 1 alkali metal. It's the first element in the 6th row, so it has 1 electron in its 6th shell. It's clearly a metal from its position. It's going to lose that electron as it ionizes. So the cesium chemically changing into a cesium ion. And that electron lost is shown at the end of the equation. Electrons lost or given up always appear on the right hand side. Meanwhile, for the phosphorus, again, check its position in the periodic table. Where's my periodic table gone? There it is. So for the phosphorus, there it is there. It's obviously a non-metal because it's on the right. It needs 1, 2, 3 more electrons to complete its shell. So it's going to become a -3 ion. So the phosphorus chemically changing into that phosphide ion. And it's picked up those free electrons, which we show at the beginning of the equation. You can always do a subatomic particle check, with phosphorus being the 15th element in the table. Oh, I lost my picture there. Phosphorus, yep, atomic number 15. So it has 15 positively charged protons. And when electrically neutral, it has 15 negatively charged electrons. So +15, -15. That's why it's electrically neutral. But come the end, you've still got 15 positively charged protons with a charge of -3, and now up to 18 electrons. The number of electrons should be the same on each side. 15 here, but 18 here. We want both sides to be 15, so we add the 3 to the left-hand side to make that happen. And finally, calcium. That's a group 2 earth metal, as we've talked about. Let's quickly show that. There's the calcium in group 4. It's got 2 electrons in its fourth shell, and it's going to lose those electrons as it ionizes. So it's going to be a calcium 2+ ion. So calcium chemically changing into a calcium ion, having lost those 2 electrons. You always show the electrons when they're no longer part of the atom. But the electrons are not part of the phosphorus at the beginning. Here the electrons are not part of the calcium at the end. Again, we can do a subatomic particle check. 20 protons for calcium. And if it's electrically neutral, the only way to get the math to work is to have 20 electrons. Then for the final calcium ion, still 20 protons. And for the charge of +2, it must be just 18 electrons. The total electron count on the 2 sides must be the same, 20, 18 plus the 2, so the electrons shown on the right-hand side to give us a total of 20. Okay, let's see, I think that's where we stopped this morning in class. Yes, it is. So that is where we will stop here as well with the online lecture, keeping pace with the pace I'm setting in class Monday, Wednesday and Friday with the 141 section 1 section. So to recap, we've got metal atoms coming together with non-metal atoms. When they come together, the electrons have been transferred from the metal to the non-metal. The non-metals become negatively charged as they gain electrons to complete their shell, and the metals become positively charged as they lose electrons to empty their shell. You can use the shape of the periodic table to realize how many electrons the metal is losing or the non-metal is gaining to make that happen. Next, we'll look at taking these metals and non-metals and combining them together to make chemical compounds and ways of realizing what the correct chemical formula will be for these compounds. Okay, good night, and I'll see everybody soon. Stay safe, wear a mask, and wash your hands.